All right, so what if I told you that the very same invisible force that powers up your phone is also the thing that makes ships rust away in the ocean, or makes fireworks just explode with color? It's wild, right? Well, today we're diving deep into the secret life of electrons and a really cool concept called redox equilibrium. So let's kick things off with a little puzzle. Think about this: a dead phone battery and a rusty old bicycle. I mean, what could possibly connect those two things? They seem like they're from totally different worlds, right? But the answer, well, it's this fundamental chemical process that's happening literally all around us, all the time. And the answer to our little puzzle, believe it or not, it's something called a redox reaction. Now, the best way to picture this is like a constant invisible dance. You've got these tiny little particles, electrons, being passed from one substance to another, back and forth. And this great electron exchange, well, that's the key to pretty much everything we're talking about today. Okay, so what is a redox reaction really? The clue is kind of hidden in the name itself. You've got red for reduction and ox for oxidation. At its core, it's a super simple idea. One thing loses electrons and another thing gains them. But here's the crucial part. It has to happen at the exact same time. They are two sides of the same coin. You just can't have one without the other. All right, let's break down the two key moves in this electron dance. First up, you've got oxidation. Now, a really handy way to remember this is the phrase, oxidation is losing electrons, that is. And on the flip side, you've got reduction. And you guessed it, reduction is gaining electrons. So one substance is the donor, giving away electrons, and the other is the acceptor, taking them in. Simple as that. Okay, so we've got this exchange happening, electrons are moving. But you might be wondering, how do we know which way they're going to go? Like, who leads in this dance? Well, it turns out chemists have a really clever way to predict exactly that. And the secret? It all comes down to something called the standard electrode potential, or E0. Yeah, that little naught symbol just means we're measuring it under standard lab conditions. No big deal. But seriously, don't let the name scare you. The absolute easiest way to think about it is like a chemical reactivity leaderboard. It's just a big ranking of how badly different substances want to grab onto electrons. Now, here's where that leaderboard concept gets really, really useful. Let's just take two examples, zinc and copper. You can see here, zinc has a negative value, right? And copper has a positive one. Believe it or not, these two little numbers are the key to predicting who is going to win the electron tug-of-war. And the rules for this are so simple, you're going to love it. Again, step one, just find the more negative value. In our case, that's zinc. So what does that tell us? It tells us that zinc is way more likely to lose its electrons. That's step two. We know zinc is going to get oxidized. And that means the other guy, copper, with its more positive value, is going to do the exact opposite. It's going to gain those electrons and get reduced. See? It's completely predictable. All right, so we can predict this flow of electrons. That's cool, I guess. But the really big question is, what can we do with that knowledge? I mean, what if we could somehow capture that flow of electrons and actually put it to work for us? Well, that is exactly how we get power from chemistry. You see, when we set things up just right to capture that natural, spontaneous flow of electrons, we create what a scientist would call a voltaic cell. But you and me, we know it by a much more familiar name, a battery. Yep, that's all a battery really is at its heart, just a controlled redox reaction. So let's peek inside one of these, shall we? A battery is basically designed to take the chemical energy from that spontaneous reaction and turn it into electrical energy. The spot where the oxidation happens, where the electrons are lost, that's called the anode, and that becomes the negative terminal of the battery. So then those electrons, they flow out through a wire, and that's the electricity that powers your stuff, all the way over to the cathode, which is the positive terminal. That's where reduction happens and the electrons find their new home. It's just a perfectly controlled flow of energy. Okay, so that's how we get power from chemistry. Pretty neat. But what if we totally flip the script? What if we use power to make a chemical reaction happen, one that would never, ever happen on its own? Well, to do that, we use something called an electrolytic cell. And this is basically the exact opposite of a battery. Instead of getting energy out of it, we pump energy into it to drive a chemical change that is non-spontaneous. We're literally forcing those electrons to dance to a tune they wouldn't normally choose. And you might ask, why would we even want to do that? Well, the applications are just huge. I'm talking about things like electroplating, that shiny chrome on a car bumper. That's this process. It's how we purify copper to be 99.99% pure, which we need for all our wiring and electronics. And it's even how we pull super reactive metals like aluminum right out of their ore in the ground. It's incredibly powerful stuff. This little table really lays it all out and makes the difference crystal clear. You've got the voltaic cell, our battery, turning chemical energy into electrical energy all on its own. And then the electrolytic cell does the complete opposite. It uses electrical energy to create a chemical change. They really are just perfect mirror images of one another. Okay, let's bring this all full circle right back to where we started with that rusty bicycle. Because rust, well, it's just another redox reaction, but it's a spontaneous one that we really, really want to stop. So the question is, how do we use everything we've just learned to win the war on rust? So rust is basically just the corrosion of iron. It's an unwelcome, totally spontaneous redox reaction. And it's not very picky. It only needs two things to get going, a little bit of water and some oxygen. When both of those are around, these tiny little electrochemical cells pop up all over the iron's surface. In one spot, the iron becomes the anode and starts losing electrons. And in another spot, oxygen becomes the cathode and starts gaining them. And the result is that nasty, flaky, reddish-brown stuff that we all hate. So if rust is just another spontaneous redox reaction, that means we can use our knowledge of that chemical leaderboard to fight back. And one of the most clever solutions is a strategy called sacrificial protection. And yeah, it sounds dramatic because it kind of is. Now here's how it works, and it's so smart. We basically connect our iron to a more reactive metal, something like zinc or magnesium. Now remember our reactivity leaderboard? Zinc has a much more negative value than iron, which means it's way, way more willing to give up its electrons. So when water and oxygen show up looking to start some trouble, the zinc basically steps in and says, hey, over here, take my electrons instead. It literally sacrifices itself, corroding away, but the iron stays perfectly safe. This is exactly why you see those funny-looking blocks of metal attached to the hulls of big ships or on pipelines. So really, when you boil it all down, the crucial takeaway is this. This invisible dance of electrons is a fundamental force of our world. And once you understand it, you learn how to harness it for good, like getting power from our batteries. But you also learn how to fight against it, to protect all the important things in our world from falling apart. So there you have it. From the power lighting up your phone screen to the rust forming on an old garden gate, these redox reactions are absolutely everywhere. Now that you know about this hidden dance of electrons, the real question is, where else are you going to start seeing it in the world around you?